Quantum computers will break Bitcoin. You've probably seen that headline. It sounds scary, but being accurately scared is surprisingly hard. What's real and what's hype? Today, I'm walking you through an interactive site I built that lets you literally play with the answer. 7 chapters, almost no jargon, everything driven by diagrams and animations. It's free, and the link is in the description. The structure is simple. Follow the tabs left to right, right now, and quantum basics, how keys works, the attack, the defense, where each chain stands, and finally, how to read quantum news without being fooled. It's available in 5 languages: English, Japanese, Portuguese, Spanish, and Korean. Watch this. An online computer and a quantum computer both try to open the same 256-bit key. Start. The classical machine on top barely moves. Brute force will take longer than the age of the universe. The quantum machine below uses Shor's algorithm, a mathematical shortcut, and finishes. But here is the crucial part. This machine does not exist. The site says so right on screen. You need roughly 500,000 physical qubits. Today's large machines have a few thousand. That's around 1% or less. So why does this matter now? Because of this. Harvest now, decrypt later. You collect data today and open it with a future machine. On a blockchain, a public key that's being exposed can never be unpublished. So this ARMI strategy works structurally. Waiting until the machine exists is already too late to start preparing. You've heard a qubit is 0 and 1 at the same time. That's this card. Face down, the answer genuinely undecided until you flip it. And it collapses to one side. But both at once does not mean instant answers. What's the treasure hunt? Every hint makes the correct box grow a little brighter. Now 6% to 47, 91, and 96. Quantum computing is really about growing the probability of the right answer. And if you overhint, it dims the game. Even the timing matters. One more reality. Real qubits are fragile. Heat and vibration flip their values at random, like this. The fix is to surround one with many and protect the value by majority vote. That protected unit is a logical qubit. Slide the cell bigger and it stabilizes. But look at the cost. About 100 physical qubits to protect one. So, breaking a key needs 1200 logical qubits. That's the 500,000 figure from earlier. Now, Bitcoin. A key is a one-way here. Private key to public key. It's easy and like rolling down here. But public key back to private key. It's like sprinting up, longer than the age of the universe for a normal computer. A large quantum computer is the one thing that could run straight back up. So what's actually at risk? Only keys that are visible. And look at this. Address types differ in when they reveal the public key. Here is a twist. Taproot, the newest format, is exposed from the start. The older P2PKH stays hidden until you spend. Newer does not mean safer. There are two attack shapes. First, stored. Coins sitting in a vault with the keyhole permanently visible. The attacker doesn't rush. They just wait for Q-Day. Then compute the key and open the vault. P2PK coins, reused addresses, Satoshi's early coins. And second, leave. The public key appears only for a moment when you spend, and the attacker races to drive it before the 10 minutes confirmation. That needs an ultra-fast machine, far harder. Run the race with less hardware and the attacker barely leaves the start line. The real concern is the stored kind, coins already exposed and simply being waited on. Studies put that at roughly 4 to 7 million BTC, about 20 to 35% of the supply. So what should the community do with exposed coins? Freeze items, leave them, and set a migration deadline. Bitcoin is genuinely split three ways. There is a draft proposal, BIP 361, about this. The site lets you pick a side and see the trade-offs. There is no settled answer yet. Now the good news. Quantum-resistant signatures are already standardized. NIST's MLDSA and SLH-DSA are finalized. FNDSA is still a draft. This is neither hopeless nor unsolved. But the new locks have a cost. Today's ECDSA signature is 72 bytes, but SLH-DSA is about 7,800 bytes, 100 times larger. Fewer transactions fit per block, so it's not a simple swap. That's why defense is a two-stage rocket. Stage 1, hide the keys. Bitcoin's BIP 360 draft. Stage 2, replace the signatures themselves, being designed across chains. We are partway through stage 1. That's the honest status. Chain by chain, and please read this as a showcase of approaches, not a leaderboard. Bitcoin. Careful, step by step, starting with the key hiding address format that breaks nothing. Ethereum. Redesign minted. The Lean Ethereum roadmap aims to rebuild on hash-based signatures. Solana, safe first. Its Winterless vault, a quantum-resistant vault, has been live on mainnet for over 2 years and is cited in Google's white paper, with a Falcon migration roadmap published too. Algorand. Algorand deployed Falcon in production where it counts most, state proofs, and QRL. QRL was born quantum resistant, using hash-based signatures from its very first block. So nobody's doing anything is wrong, and so is somebody already finished. The most practical chapter. Real headlines, 3 buttons. Generally important, progress but misframed, or just FUD. Take quantum breaks Bitcoin in 9 minutes. That means FUD. Google's estimate is confidential. First, if you had a 500,000 qubit machine, dropping the promise is the classic tell. And here is my favorite experiment. Remember 15-bit key broken on quantum hardware. Swap the quantum output for plain dice and watch. Both reach the key. Tiny keys are solvable with randomness, so how many bits proves nothing. What to watch instead? Progress in error-corrected logical qubits. Let's wrap up. Nobody knows when Q-Day arrives, but change the question and everything gets clearer. Not when does it break, but will the defensive migration finish first? Neither panic nor dismiss. That's quantum edge literacy, and that's what this site is for. Link in the description. If it helped, a like and subscribe generally helps. And tell me in the comments which chapter clicked for you. See you in the next one. Bye.